video showing a comparison between a neuromorphic vision sensor and a standard camera. So on the top left is what you see, the standard RGB. This is a rocket launch, and below that is the simulation of that particular scene. And this is the so-called event-based sensor or the neuromorphic sensor. I'll play the video again, don't worry about that. What is more important is you don't see the background with these neuromorphic sensors. What you actually see is only changes that are happening. Each pixel is sensing the changes independently of each other. So you get to see the clouds, you get to see the rocket launching. And then when something interesting happens, like a cow stampede, you get to see that in the neuromorphic vision sensor. So this is actually how our eyes work. They pick up only changes. And that's what this neuromorphic vision sensor is trying to also emulate. So essentially, neuromorphic engineering is at the intersection of 4 different research fields: neuroscience, signal processing, robotics, and AI. We can get to brain-inspired processing. We can get to sensors that work like our eyes, sensors that work like our ears, and so on. Eventually, we want to tackle real-world problems, and that's also something at ICNS we take pride in. Whatever problem that we work on, we have a real-world impact. And you can ask me this question: hey, what is an example of a neuromorphic system? You might have used a Logitech mouse with a marble behind it for tracking the position of the mouse. That's actually invented by the director of our institute, Andrevan Sheikh. And it's one of the earliest devices that are neuromorphic. And this market is primed for exponential growth in the next 5 years or so. Key players like HP, Google, Samsung, Sony have already invested a lot of money in this market. And we expect Middle East and Asia to play a crucial role moving forwards for this exponential growth. And let's also look at what spiking neural networks are and how they are different to conventional convolutional neural networks. Spiking neural networks are the bread and butter when it comes to event-based processing on neuromorphic chips. Convolutional neural networks, on the other hand, are what we are used to for image processing, computer vision, and so on. That makes use of matrix multiplications, ReLU layers, pooling layers, fully connected layers, and so on. And most of it is quite math intensive, so we need GPUs to train these CNNs and also do inference on specific ASICs or TPUs. Whereas spiking neural networks are event-driven. You get a stream of spikes at one end, and then you have an integrate and fire neuron, and that also gives a stream of spikes at the other end. So this is math-like based on threshold logic and quite hardware friendly. So I just introduced to you what neuromorphic systems are. Sensing, processing is all done in an event-based fashion. So evolving neuromorphic systems, as proposed in this paper, is taking this idea one step forward, where we are now letting the systems, the neuromorphic systems, behave much like how we have evolved over time, competing against each other for resources, competing against other species especially. So imagine we have a DAO, or a decentralized autonomous organization. It could also be an individual entity in the world, enabling a smart contract competition where they have devised a particular task for this neuromorphic system to perform at a particular level. Now, different people from around the world, neuromorphic researchers, would be able to sign up for this smart contract and then compete against each other for several rounds, much like how evolution works, and get the reward. And once they get the reward, or once we have reached the smart contract thresholds for the end of the competition, the tasks themselves can change. They can evolve. And thereby the nodes again have to evolve to the new task, maybe increased difficulty of the task. So we can have different point rules for reward, but essentially the purpose of the host or the smart contract decides whether there'll be more punishment or whether there'll be more focus on the reward when we have the incentive mechanism devised or hard coded into the smart contract. And all this is made possible because of blockchains. We can do it in a centralized setup, but that really defeats the purpose of having a competition which is not controlled by a single entity. So let me talk about the properties and the spiking neural networks that we have used to test this framework. So this is a standard camera and an event camera looking at a rotating disk with this black dot. The standard camera is going to capture an image at regular intervals. But the DVS, or the dynamic vision sensor, or the event camera, or the neuromorphic vision sensor, is only going to sense changes when the rotating dot within that disk is encountering the pixels. So if it rotates fast, you get events faster. If it doesn't rotate, you get no events. And that's what this equation shows. If you get an event at a particular pixel and the intensity changes and reaches a certain threshold, then you get an event at that particular location. So we can achieve asynchronous processing, spatiotemporal sparsity, and a model that is also spike-based. We can now make use of a spiking neural network to encode a data like this. This is a DVS gesture recognition data set. And this is, again, publicly available. We have just made use of this data set to test our evolving neuromorphic systems framework. This is one of the spiking neural networks that we employ. It's called Slayer. It's a fairly well-known method within the neuromorphic community. I won't go into the details. You can look into the paper for what Slayer does. And we also have a second model called asynchronous sparse convolutional neural networks, which exploit the spatial and temporal sparsity of the data. Again, I won't go into much details for lack of time. And we also have another model called inceptive events time surfaces on top of the asynchronous spiking CNNs. What is more important here is, for the sake of this presentation, just know that we have three different models that are competing against each other. So let me go into the smart contract implementation details. The goal of this ENS system is to incentivize successful modeling, to solicit better neuromorphic machine learning models, especially considering the niche research domain and the availability of neuromorphic data in general. So there are three stages to the smart contract. First is the deployment stage, where whoever designs this will also provide some sample training data and upload it onto the IPFS. Provide the hash of the sample training data and the secret test data that they are holding back. The hash of it has to be uploaded onto the smart contract so that it's fair for the users. I'll get to this point later, but for now, we know that the smart contract has the hash of the sample training data and the secret test data. Once we do a round of testing on the mainnet, we can deploy it. And the modeling stage is when different wallets register for the smart contract, do the training locally. The training does not happen in the blockchain. And this goes on for several rounds, and the model updates happen, and the IPFS models are being updated. And once this deadline is reached, we can go to the reward phase, where once a certain threshold is met, a baseline performance is met, we don't penalize the wallets. We give back the registration fee that they initially deposited into the smart contract, and also rewards if they meet performance above the baseline. The model will forfeit the deposit if they perform below the baseline, if their model performs below the baseline. And this is just the minimum performance that we expect, not like the highest performance that the smart contract requires. So this is the testing of that particular idea. The smart contract owner uploads the training and the test data set to the IPFS, updates the hash into the smart contract, and shows that address in the smart contract and deploys it. So modelers can now download the training data. They can also use their own training data to train their models. They're not restricted to the training data that the smart contract owner provides. And they can do their modeling process by starting their deposit into the smart contract, getting the model information from the IPFS, getting the sample training data, and so on. So the reward phase will just
1 minute.
Yes,
I think
okay, cool.
Yeah.
So the reward phase is just looking at the accuracies based on the secret test set, and then rewarding the modelers based on who gets the best accuracy. So the key point here to note is both the smart contract owner and the modeler are aware that there's a secret test data, but it's not available to them at the beginning. Only after several rounds of testing, and only when the reward phase happens, then the smart contract owner releases the test set, and then the modeler can verify the accuracy that their model gets. So it's fair for everybody. So I'd like to take a step back and say that all this is just proof of concept simulation. We can have more complex real world scenarios embedded into this smart contract. And this is just one of the papers I have in this conference. And we have another paper that I will be presenting shortly. But before that, I'd like to take questions if there are any.
So is there an implementation of this idea? Looks like you're using Ethereum.
Right. So we do have an implementation that accompanies the paper. You can take a look at the GitHub link.
Okay. And what are some like use cases you're looking at?
So we are trying to do gesture recognition based on the models that each person provides, and perhaps do some sort of federated learning. I haven't incorporated this federated learning concept into this paper. That's the idea that we are discussing next.
Okay, perhaps we can move on to the next paper. I can ask the remaining questions I had. Thank you. Thank you, Bharat.